Good morning, everyone. It's really an honor to be here to give a talk in IWACOM. Especially, I appreciate for our invitation Professor Wada, Professor Asai, and Professor Mitsumi. I'm Chanwook Park, a final year PhD student at Northwestern University. Professor Wing-Kam Liu is my academic advisor, and he's also a co-founder of Hidden AI, which is a startup based on our research works. So today, my talk is about interpolating neural network, a new network structure based on our series of works that has been over 10 years. We want to bring up and integrate the numerical analysis and tensor decomposition and artificial intelligence to revolutionize the way we program and approach scientific and engineering softwares. Now, let me get started. I'm going to bring a simple motivation where we started from. So I first want to coin this term software 2.0, first coined by this guy, Andres Carpati, previously a senior director at Tesla. Now he works in OpenAI. So let me listen to what he says.
I kind of saw something remarkable happening in software development and how a lot of code was being transitioned to be written not in sort of C++ and so on, but it's written in the weights of a neural net. Mm-hmm. Basically just saying that neural nets are taking over software.
Neural networks are taking over software. So based on his definition, software 1.0 is a traditional way of programming a software. Developers specify each task and runs task by task. However, in software 2.0, we want to integrate everything under a vast size of network and do the training to get the software. And we also have witnessed a lot of improvements in engineering software, such as physics-informed neural networks or operator learning things. However, at the same time, we also face challenges in both computer science and engineering fields, although they are a little bit different. So in computer science, we all know that the computational resources is growing exponentially over time, thanks to this gentleman, NVIDIA. But we also want to point out that we are facing sustainability issue, energy consumption. So I want to listen to what Lisa Su talks about it.
And so this fundamentally says our challenge is to figure out how over the next decade we think about compute efficiency as the #1 priority.
Yeah, this is what computer science now faces challenge. However, in engineering field, we are facing something different, such as data-related issue, where multimodality data are everywhere, experiment and simulation. And especially for simulation data, we are dealing with high-resolution data, which requires a lot of storage requirements. Another issue is the accuracy. So like this physics-informed neural network, in general, they cannot achieve the level of accuracy that classical numerical methods can do, like finite element. Finally, if we think of the real-time application, we need fast inference, like robots or manufacturing control. However, as the neural network deepens, the inference time is pretty long than what we require for the control applications. So with engineering software 2.0 and interpolating neural network, we would like to address all these challenges altogether. So here is a very simple motivation of our work. Let's think of a very simple regression problem. We have 90 data points here. And I want to do the regression using neural network. Third hidden layer, 10 neuron, and value activation functions. And the blue lines are the results. And also, we want to do the same thing with piecewise linear regression. So this is based on our mathematical intuition. Okay, this data, we can regress this data with 2 linear lines. That is this. And in this piecewise linear regression, we want to optimize only 3 points. This one, this one, this one. Basically, we're going to optimize 6 values to find out this relationship, which is much more efficient. So if we check the metrics, the loss function, the error, is almost the same. But the number of parameters reduced down to 200 to 6. meaning that this is much more efficient. And why we could do this is because we leverage the idea of our mathematical knowledge. So this was the motivation of our work. So let me briefly expand this problem to this one. So we made this data given the temperature and number of coffee cups sold. And given this data, we want to find out how many coffee cups will be sold when the temperature is 57 degrees. In computer science, what people think of interpolation is just draw the data points, there are 10 data points, and draw the line in between them, and find the corresponding value. And what is actually the limitation of this approach is the overfitting, right? If we just directly go through those data points, then we'll severely overfit the data. In our network, in INN, we view some slightly differently. Instead of blindly linking the data points, training data points, we want to create interpolating points with divided segments. This is before training, and now we want to train these red dots like this. And in terms of the neural network architecture, this is a pruned network where the weights and biases are functions of x and u. They are not just randomly changing values. They have mathematical functions. I will go into detail for this, but yeah, this is a key brief introduction to INN for one-dimensional applications. So we leverage this idea and apply this to engineering software 2.0 that can unify training, learning, calibration, and solving. And this is an alternative to the traditional data-driven approach that can revolutionize what we have done so far. So this is a very brief diagram of interpolating neural network. So we actually build a functional space in INN. This is what we are good at. And given this network, we just set the data loss, like mean square error, as a loss function, then it's going to be training. If we set the loss as a PDE, partial differential equation, then it's going to be solving. If it is to the calibration, if we use the train and solve model to do the inverse analysis, then it's going to be calibration. So using this INN structure, we can solve a lot of different applications, not only in engineering domain, but we can also in computer science domain. I want to show you everything in this talk. Okay. So let me go a little bit on the into the deep of this 1D interpolation, piecewise linear. By the way, yes, this, it doesn't move. Anyway, so this is a mathematical form of the piecewise interpolation or piecewise linear regression for element E, which is exactly the same as linear finite element shape functions. In neural network architecture, this segment, for one segment, we can view this as this, where the weights and biases are not random numbers, but they are functions of nodal coordinates, x and nodal value, u. So if we just draw it, it's just nothing but linear function. So basically, the first line is this function, and it will be multiplied with u of e. And the second function is the second line. It will be multiplied by this value. So it's a stacking of these hierarchical segments to build this linear interpolation. All right, now we want to move on to one step further, which is the nonlinear interpolation. How we can do the nonlinear interpolation? The idea is simple. We want to add one more hidden layer. In this hidden layer, we call this as convolution patch function. So there's a mathematical details we borrow from classical interpolation theories and mastery theories. I don't want to go into the detail on the mathematics, but we can refer to this paper if you want to study more on this. But this third layer is where the magic happens. So by just adding this third layer, we can do the nonlinear interpolation by leveraging the neighboring nodal information. So we do the same thing, stack the element segment-wise network, and finally define the loss function to solve or train whatever we want. So let me give you a brief comparison between linear and nonlinear segments approximation. So in the linear training, I borrowed the same problem. Let's say we have 90 data points, and we want to go over one by one. So let's say this x of k, u of k, this is k's data point. And for this data point, we want to first measure what is corresponding. Let me annotate here if possible. Yep. What is corresponding function value at this? How we can do this? It doesn't work. Okay. How we can do this? We compute the interpolation function value at this node, node 4 and node 5, just like linear FEM, and multiply this with nodal values U4 and U5. This is for data point K, and we want to loop over the entire 90 data points. So that the loss function is defined like this. And finally, we just minimize U1 through U6, 6 points, and that's it. This is how we train this problem. For the nonlinear application, there's nothing new or different except for that now we want to consider more neighboring nodes to build the interpolation function. So in this case, I want to consider 2 on the left side and 2 on the right side. So instead of having 2 interpolation functions involved, now we have 5 interpolation functions and 5 nodal values involved. So we are expanding the connectivity among those those red points, red dots. And rest of them are the same. So still, we want to optimize only 6 values, U1 through U6. But the functions are different. Functions are now nonlinear. If you just compare the metrics, they're really similar. Right? The loss function value and these one are similar. The parameters are the same, and speed are the same, but compared to the neural network, where we required over 200 parameters, now we can do the same, much better with only 6 parameters, 6 trainable parameters. This is a huge difference. So let me summarize the 1D interpolation things. So we started with linear interpolation, right? Piecewise linear, where we had only 2 hidden layers. And given this training setup, we have 5 segments, right? 6 nodes. We do the training. And this is what we got for the linear interpolation. We can also interpret this as a graph operation, where we have 6 nodes, and the way we build the interpolation function can be viewed as a message passing in graph network. In this case, since we are only considering one neighboring nodes, it's going to be considered as a one-hop message passing. Now, if you want to do the nonlinear interpolation, we just add another layer, third layer, and at the same time, we are expanding the domain of influence. Now, our interpolation function has a wider domain. Interpolation domain. That means we are having higher connectivity, right? So this is context supported interpolation. And finally, we can keep increasing the domain of influence until it covers the entire input space, which is a non-local approximation, or it can view this as a global approximation. In this case, we don't even need the first 2 layers because it covers everything. Something like this. This interpolation function covers the entire space, right? So we can, depending on the connectivity choice, we can start with a local approximation, or we can go to the global approximation. That is the capability of INF for doing this kind of interpolation. Right, next. Before I go to the next, now I want to go into the high dimensional problem. Now this is only 1D problem, like single variate. We can also do the same idea for the high dimensional problem, but we can only go up to, we tried up to 3-dimension space, input dimension, because the interpolation cost grows exponentially as the input dimension grows up. So think of the full 3D finite element simulation. We can do up to that, but we cannot go over than that. So how we can deal with this curse of dimensionality for high dimensional input space? This is where the tensor decomposition comes to the picture. So the tensor decomposition is a mathematics, basically. Tensor decomposition expresses a data tensor or multi-way array as a sequence of elementary operation acting on a simple tensor. So we can look at, there are a lot of different tensor decomposition methods, and among them, I want to just introduce a CP, canonical polyadic decomposition, one example. So here's the idea. Given third order tensor, which has J1, J2, J3 discretization, we want to approximate this as a summation of 1D vectors, 1D tensor products. So in the schematics, given this J1, J2, J3 discretization, we want to approximate this as a tensor product of 1D vector, 1D vector, 1D vector. And keep going. We're just adding modes. And finally, the largest one, largest mode is large M. Oh, actually one more. So this is the standard tensor decomposition, what mathematicians think of. And now we want to do this tensor decomposition for the functional approximation. What we have to do is bring this tensor in the coordinate domain. Like this. We just added a coordinate system which is discretized with J1, J2, J3 nodes. Now, still, everything is the same. But when we want to find out the function value at a specific grid point, what we can do is we just multiply the corresponding vector value, right? Scalar, 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 just multiply, and do the summation for different modes. So something like this. Oh, sorry. Unfortunately, this becomes so slow. Yeah, this one. So if you want to measure the function value at specific grid point, what we can do is just do the multiplication of this vector value, I mean the scalar values for each vector, and do the summation. But this way, we are only limited to measuring the function value at the grid points, right? We don't know what is going to be the function value on the non-grid points, something like this, right? Look at the red ones. If you want to measure the function value at x1, x2, x3, which are not on the grid points, now what we can do is do the interpolation. We want to do the interpolation in 1D vectors only. And for this interpolation, we're going to leverage exactly the same thing that I just showed you in the previous slides. So in this way, we can reduce the computation cost significantly, because now we're going to only deal with 1D vectors instead of high-dimensional tensors. So to summarize, for multivariate cases, we can do the fully coupled interpolation, just like we can think of this as a finite element, full 3D. However, as I told you, we are limited by like 3-dimensional input space. If it is larger than that, the cost is significant. We cannot solve. We cannot do it. So we propose a fully decoupled, tensor decomposition. So I call this as fully separated. Or you can mix both of them. So some variables go into the fully coupled interpolation, while the others go with the separated interpolation. So these are the possibilities, versatilities that INN can take. And among them, I just want to focus on the tensor decomposition and show you the significance of it. So compared to the feed-forward neural network, or MLP, the total trainable parameter grows quadratically with the number of neurons, right? This is J squared. However, with the full tensor decomposition, it grows linearly with the level of discretization. This brings us the difference. We can reduce the training parameters. Now I want to introduce you some benchmarks, problems that we solved. The first problem, of course, this is a training problem. The first problem is we want to generate, given the physical equation, which has 10 input and 5 outputs, we want to generate the data based on this equation and do the training and measure the accuracy. So in this case, we have 5 outputs, and each output has a physical meaning, something like this. And I don't want to go into detail, but let me compare the benchmark. So we generated 1 million training data based on the physical equations, and compared with XGBoost, one of the best algorithms in ML community, neural network, INN linear, and INN nonlinear. As you can see in the table, INN has the smallest trainable parameters, but having best accuracy and very fast inference time. And also, this XGBoost is based on the tree structure. That means we cannot do the automatic differentiation on the trained surrogate model. However, in our case, we can do the automatic differentiation as it is, meaning that we can apply this to calibration problem really, or inverse design optimization really easily. We also solved classification problem compared to support vector classifier and neural network. Ours having the smallest trainable parameter, best accuracy, and shortest training time. And then we applied our INN train model, which is on the left side. We actually solved the same problem to do the inverse design optimization. In this case, in the inverse problem, we want to optimize the ground truth value of x3 and x4, which are 0.5 and 0.6. So in this optimization, if INN returns a value close to this one, it's going to be good. So as you can see, compared to FFNN, we are having smaller error and reliable prediction, a lower standard deviation among different initial guesses. This is all because that INN is much more accurate than other machine learning methods for training data. Okay. Now, I want to pause a little bit. So up to now, I introduced the concept of engineering software 2.0 and INN, and cover training part and calibration part. Now, the only thing left is the solving part. Okay? And for this solving, we can solve many different engineering applications. I want to go briefly at each of them in the remaining time of my talk. So let's first start with a full interpolation, like finite element methods. In general, INN with full interpolation, we called it as a convolution, C-hidden convolution hierarchical deep learning neural network. This is from my paper. So let's think of this FEM, three-dimensional FEM. We have linear element and 700 nodes. And what people do in FEM to increase the approximation order or polynomial order is they just add more points for every element. It ends up to be, for example, if the order is 4, then it ends up to be over 35,000 nodes, which is, I would say, 50 times more? No, 100 times more? Yeah, a lot. So this one grows exponentially. Finally, we'll end up with a matrix equation with large matrix size and small bandwidth. However, with INN or C-hidden, we still use the same linear elements, but we're going to leverage the neighboring element to build the higher order interpolation. So when order was 1, give me 1 second, where's my mouse? Yeah, when the order was 1, it's still 700 nodes. When the order is 4, we are still working on the same nodes. But now we are increasing the connectivity between the metrics. That results in this one. So we're going to have a smaller metric size, but larger bandwidth, more connectivity. This brings us the benefit, because we don't want to solve high degrees of freedom problem, because we are limited by the memory space. So this benchmark shows a comparison between finite element and running on ANSYS and our C hidden. So as you can see, the dotted lines are the finite element ANSYS, and solid lines are our C hidden. So as you can see, for small degrees of freedom, small DUF problems, ANSYS finite element is more efficient. But we can see the crossover as we refine the mesh, right? So for higher degrees of freedom, we can be much faster than finite element softwares. This is a 3D linear elasticity problem. All right. So this example is the C hidden or INN with full interpolation. I didn't talk about tensor decomposition for solving part. Now we want to move on to the tensor decomposition. How much we can go farther than this FEM or C hidden. So with the tensor decomposition, it's phenomenal. It's really significant. So this was the range of FEM, the black lines. But with tensor decomposition, INN tensor decomposition, we can go up to 10 to the 21th power grid points, which is insane. So with tensor decomposition, 3D elasticity, we can solve 1 million cube problem, which corresponds to 10 to the 18 DOF exascale problem less than an hour, and 10 to the 21st power problem, zetascale problem in a day. And if you are familiar with finite element, using standard finite element, 10 to the 10th power or 10 billion DOF problem is almost the limit of our state-of-the-art supercomputers. So this is a benefit of tensor decomposition for solving linear elasticity problems. However, we don't want to stop here. We want to go further to solve data-driven problems or parameterized problems. So in this case, we are only dealing with 3 inputs, x, y, z, space dimension. What if we have time and other parametric dimension, like material properties or parameters in the source term of your partial differential equation? We can also solve it using the same framework. So let me compare to the traditional data-driven approach and ours. So in traditional data-driven approach with finite element simulations, what people do, including the ANSYS AI, we start with physics, data generation, meaning that we do the sampling in the parametric space, run FEM simulation many times, gather all the data, and train the data as a surrogate model. And given the surrogate model, we do the inverse optimization. And in this offline step, we have a lot of challenges. Expensive run for a large mesh, large number of simulation required, large disk storage required, unstable training accuracy of the surrogate model, right? But instead of doing this, yeah, you can see here the number of sampling points grows exponentially, as we all know. Instead of doing this in INN, we want to solve all together, x, y, z, and time, and parameter space. So let me give you an example. This is a simple heat conduction example with parameter k, conduction coefficient, and source terms. And this heat source term are actually we are simulating the additive manufacturing problem. And this heat source term has some parameters, laser power and something like this. So in general, this problem is 9-dimensional problem. And we discretize this with 1,000 segments or 1,000 elements in each direction. In FEM, this corresponds to solving 10 to the 27 power degrees of freedom. Nobody can solve, at least in 10 years for now. We try to solve the same problem with PINN. Unfortunately, PINN stopped converging after 7 inputs. They cannot solve up to 9 input variables. It doesn't converge. And also the number of collocation points grows exponentially, which is really challenging. But with INN, although we are having a fairly large amount of parameters, but it is still less than 1 million, but we can solve it in 2 hours. So you can see a video here. This is the result that we have. So our solution is, okay. I want to also point out this one. Disk storage. This is really small because at the end of the day, what we store is just 1D vectors. This is only in a megabyte scale. And once we have this 1D vector stored, then we can inference among entire input space, including space, time, and time and parameter. That is the key difference between traditional data-driven methods and ours, especially for solving. So finally, I think this is the last example that I prepared. We apply the same thing for topology optimization. So in this case, we compare with finite element methods based topology optimization. But in this case, we solved up to 1 billion degrees of freedom problem. And of course, with FEM-based topology optimization, we can never solve it because the time required is 10 to the 6 hours. But with our tensor decomposition technique, we are able to solve it within 100 hours, in 100 hours. This was all because of the benefit of tensor decomposition. And because of this, we are able to solve much challenging problem, like this drone design. So this is a multi-scale topology optimization problem where each region having different cost function, different requirements. And you can see the details of this work in this paper. This was done by my previous lab mates. All right. So I think now this is summary slide is left. So today I introduced our new neural network architecture, interpolating neural network that actually enables the vision of engineering software 2.0, the next level engineering softwares. And I really appreciate my group members, including Professor Wing-Kam Liu, and these are all the collaborators of mine. And I appreciate my funding sources, including NSF and NIST. Finally, I'm going to graduate next summer, so I'm open to the job market. And if you want to have more questions, personal questions, this is my contact information, so you can take a photo or picture, capture on it. You can contact me at any time. Thank you so much for your concentration, and I'm open to the question. Thank you so much.